Hello friends, in this video we'll see how to model the core losses of the amorphous and nanocrystalline code in the Ansys. Uh, the modeling of core loss for this type of code is a bit involved compared to the other types like ferrite and electrical steel. Uh, in the We'll see why it is so. Uh, for now, let's just start with the modeling in the Ansys. I have this model where you can see the transformer model. Here you can see the red is the primary winding and yellow is my secondary winding. Right now, I don't have a core in this model, and the primary and secondary winding I have created using the tool called PMag. Uh, in subsequent videos, I might take this topic, how to create a model in a PMag and how to export it to how to create a Ansys Maxwell 2D or 3D design using the PMag model, which is simple compared to directly start modeling in the Ansys 3D. You can see to create these bindings, it's quite a bit of, it will be quite a bit of a headache. So we can leverage the tools like PMag to do so. Uh, Now I'll just run a one script, a Python script to create a code. Uh, and now let's see, start. Now you can see script started running and it's creating a model, core model. So how to create such script and edit it? I have recorded one video on that. You can check that out. Uh, for now, I'll just move ahead with this. Uh, I'll show just to give a brief overview. I'll just show the script. So this is that script, modify code. You can see this is some starting commands, and what we're doing, we are creating a polylines, then we are covering it to make the faces. We have created a multiple polylines to do uh, to create one single code, and finally we have united them. Here you can see. Finally, it unites and creates a one part of a code. Like that, I have created a four code. Uh, four, and finally we get this geometry. The core, uh, it's a single core. I have divided into four parts. So before going deep dive into it, we'll just see once how the amorphous core are made up of. So if you see here, you can see a picture of amorphous core. Here you can see these layers are basically lamination. So the laminations are arranged are stacked up on top of another like this. Second one will come like this. It will be a continuous lamination. So the layers, you can see this is one lamination layer. And I will also, I would like to talk on one more phenomenon, which is this orthogonal flux. So here you can see these are the planes of the lamination. They are like this. And the flux passing or the flux density going passing like this, the eddy current due to that will flow in this way. And because the lamination thickness is quite small, we can limit the eddy currents. And so we can reduce the eddy current losses. But in our transformer, this is the basically path of a magnetic field for the magnetizing flux. But for the leakage, flux will pass like this. So it will be perpendicular at this point. It will be perpendicular to the layers of the lamination, and will create a eddy current. And there is no the laminations are because are like this, so there is a free circulating path for the eddy current, and this would create a lot of losses in the core. Thus, to model this effect properly, we have to uh, uh, model it accordingly in the Ansys. So, as you can see, I have divided core in four such parts because the laminations here will be in this way, while here laminations will be like this. And while modeling in the ANSYS, we have to define the plane of the lamination using its normal vector. So for it, normal vector will come like this. For this, normal vector will come like this. So that's why I have created a, you can see, four cores. Uh, now let's just move ahead and we'll start defining the material. Now for this two, we assign a material. Hmm. Uh, core underscore v. This is the one material I have already created. So I'll just show how to do that. I'll go and editing started it. This is the relative permeability I have kept for the material. I have the data sheet of the material. Uh, it's here, and here you can see uh, my peak plug density. I have designed such a way that it will come around zero point 0.2 Tesla, and for and minimum will be 0. So I kept average permeability around 6500. And other parameters like density and resistivity I have taken from here. Which is here in ANSYS we have to define the conductivity. So bulk conductivity I have defined 76.923 Siemens per meter, and similarly uh, mass density 7200. Here it is in gram per centimeter cube. I have converted into meter per cube, kilogram per meter cube. It will come around 7200. So when you start with it, here the core loss model won't be specified. It will be set as a null. So what we have to do is also the lamination, it will be by default, it will be a solid. So in this way, when you start creating a new material, these will be the parameter it will show like this. So first we have to do core loss model, we have to set to the electrical skill. Now you can see all coefficients are 0, 0, 0. Then composition, you have to make lamination. And we have to define the axis of the lamination. Now here you can see we are, the core are, the planes of the lamination are in parallel to the XY plane. So the lamination, the orthogonal vector will come in the Z direction. So we have to define in that way. So stacking direction, we have to select V3, which is a Z vector. And the stacking factor for amorphous 4 usually comes around 0.84. So we'll keep that. And now here on the bottom side, you can see the calculate properties for a core loss at one frequency. We have to select this option to define the core loss model. Now I have this existing data set. What I have done is uh, I have this core loss model available from the manufacturer, Magging. I have contacted them and they have given me this core loss data. Usually it is also available in the data sheet. Here you can see the same data what they have given here in the tabular form. It's shown graphically in the data sheet. Usually this kind of curves, DP curve they call it, are given in the data sheet for the different frequencies. You can see the core loss on one axis and plug density on another axis. So you can follow this graph, you can calculate the core loss at each point. Let's say choose the frequency for my application, it's 25 kilohertz. So on 25 kilohertz, you will choose this line. Along this line, you will take a different point. I have the data for that points at 25 kilohertz. This is the data, so I have used it here. Here you can see. And one more thing, important thing you should do is you can export the dataset and just export with the name. Let's say I'll give its name as a core loss data. So you can use that data later on if you need, or if you are creating a one more model or one more material, and it is using the same one more core you are creating, and it is using same type of material, you can use this data once again. Here I have specified the core loss unit. Note, these are not a default value. I have the default value here will be 60 hertz. I have kept it as a 25 kilohertz. And the thickness for usually for amorphous core, they use a 25 micron sheet. So I have specified it here, and again the conductivity value, what we have seen before. So let's just hit OK, and done. Yes. Oh, sorry. The one mistake I have done here is I have chosen core V for this. So let me rectify that mistake. I'll choose core H for that. And all other parameters you can see are same for it. Just the direction here I have kept V3 for core H. So, and V4 core V also the direction now V3 because I have changed it later on, but I'll select it as a different direction. I'll subsequently I'll show what is the meaning of core H and core V. Basically, core H I am choosing it for two horizontal core and core V for this two vertical core. So let's just go ahead with the core H. Now I'll choose this core for these two cores, and let's define material for these two cores. So I'll select core underscore V. So this is the core, but I'll edit the properties. The all other properties, relative permeability, bulk conductivity, KH, KC, KE are same. Again, this mass density is also same. Stacking factor is also same. Just the direction. Stacking direction is now in a y direction. I'll choose V2. Also, I'll show one more time this core loss at one frequency. We'll calculate. We have this existing data. So let's say you don't have this data. I'll just make it all 0, 0, 0, 0, 0, 0, 0. This is the, by default, it will come like this. But then in a previous, while creating a previous core, we have exported that data set. We'll just import that. And once we import, we have all the core data ready. And don't forget to mention this parameter. And let's just go ahead. Okay. Okay, done. And now we have to, to measure the core loss, to calculate the core loss, we have to let Ansys know that we want to measure that. And so we have to set the core loss. So here you can see for core 1, 2, 3, 4 materials, the core loss model is defined, but we have to choose this. We have to select this parameter. Once we select it, Ansys will start. The core loss model is now enabled for the calculation, and in the while simulation, Ansys will use this data. Now let's just start the excitation. What I have defined here, you can see. I'll just show you. Primary excitation I have given here. Initial current, resistance, inductance I have defined, and I have used this PWL periodic. It is a square wave I have defined. Maybe in later part of the videos, in other videos, I will show how to create this, any random shape waveform, how to create it. Right now, I'm using a square wave with 25 kilohertz frequency, and its amplitude is 500 minus 500, goes from 500 to minus 500. And in secondary, I have given a current 8.49 ampere sine wave current. I have given. So setup is already defined. Uh, so we'll just start with it. Before that, what we'll do is in the result, go to the create a field report, rectangular plot. In that, we have to choose. Sorry, choose anything wrong. Report. We have to create transient report, not a field report. Rectangular plot. Huh. In this, we have to choose this core loss, eddy current loss. Uh, we'll choose all these parameters and we'll create a new report using it. We'll just rename it as a core loss. Okay, so here our plot, it will show our plot. Now let's just, before going ahead, let's just validate our design. So we'll get to know if any errors are there in the design. It's okay. So eddy effects are not set in this design. So it's showing eddy effect setting. We need to revisiting due to the recent changes in the design. So we have to go again, assign excitation, set eddy effects, and we'll enable eddy effects for all except the core. Your core will be there. We have to disable this because why is it so? I will just uh, show you why I am doing that. We'll go to help, Maxwell PDF. If we choose this, and I'll just search core loss. This is very useful PDF in and all the things you need uh, to handle Maxwell to do the model creation, simulation. You can refer this help at any time. What I want to do is these are the stacking diagram X, Y, Z, what we have defined 1, 2, 3. I just this is the core loss model. So, here is that one phenomenon I explained here, which is the extra eddy current loss due to the orthogonal flux. Ansys does model that additional core loss due to the flux normal to the lamination. But for that, eddy effects must always be turned off for the laminated object. This option, we have to turn off the eddy effect for that laminated object, that is our core. That's why when we were setting the eddy effects, we have unchecked this box. Now we can just start with our setup, analyze, and it will start the simulation. Now you can see the simulation started, and I'll just fast forward this. Here you can see voltage start coming, started building across the winding. The 500 volt what we have given across the winding. It's a square wave, it started generating. And this is the core loss. This is core loss started generating. I'll just fast forward it. We can see we are successfully modeled the core loss in the Ansys. That's it for today, guys. In the next video, I would like to talk more on a different application for IronPython script, and we will see how to modify that script using ChatGPT. It would be an interesting topic, guys. Hope you enjoyed this video and stay tuned for the next.